All right, let's begin. How's everybody doing? Good. All right, so we didn't have class last week, but hopefully you were able to keep up on things by watching those videos. I didn't get any emails from students while I was gone, and so that either means that the videos were so clear that you didn't have any questions, or so confusing that you didn't know where to begin. So I hope it was the first of those two. I sent out a message earlier today pushing back the homework submission deadline until 2 p.m. And the reason why isn't because I thought you needed more time to work the problems, but rather I wanted to make sure that you uploaded them as PDF files. I think there were a couple of students, not many, but a few who uploaded them as image files, and that makes it really hard for the grader to review your work when they're uploaded as individual image files. And so it needs to be a continuous PDF. I've told the grader to only grade the assignments if it's as a continuous PDF. Now I know sometimes you need to upload like a second version, like you notice a mistake in the first one, and that's okay. I always set these assignments so that you have unlimited attempts. Hopefully it doesn't take more than 2 or 3 times to get it right, but I guess in theory you can do 100 or 150 or whatever, but at least they should be PDF files. So any questions about the announcements? Okay, your next homework set is due on Tuesday the 12th of September, so we've got some time to get started on this first stuff related to Chapter 3. So if you're following along in the book, that we've moved on from fluid properties, which was Chapter 2, and now we're going to be doing hydrostatic equation, which is the main idea in Chapter 3. All right, so pressure, the variation of pressure. Just as a review, there are 2 ways to think about the pressure at a certain location. Here we have a tank of water, and this little triangle that's at the top of the tank and then the secondary lines below the water surface, that's meant to indicate that it's open to the atmosphere. So just to remind you what some of these different little technical drawing notations are meant to indicate. So we have atmospheric pressure above the water, and then as you work your way down through the water, the pressure is increasing at the rate of gamma. So unit weight, you can think of unit weight as how quickly pressure is accumulating, because the units of unit weight, for instance of water, this is a great marker, 9810 newtons per meter cubed. And so what that means is every meter that you go down through there, the pressure is accumulating by 9810 newtons per meter squared for every meter of depth. So here, the 2 ways I'd like you, just as a refresher, to solve the pressure at location 2 is according to the full hydrostatic equation, where you say, I know the pressure at 1 and I'm solving for the pressure at 2, so P2 is the unknown. You've got a Z value that is, we could say the bottom of the tank is our datum. So here's Z equals 0 is the bottom of the tank, so you need to know Z2 and Z1. So that's the full-fledged hydrostatic equation, but then the sort of more abbreviated hydrostatic equation says, let's assume that the pressure at 1 is 0 relative to gauge. You know, in other words, atmospheric pressure is our baseline, and then as we go down, pressure increases. Okay, so I'm going to pause the recording for just a moment, and in your notes, I'd like you to briefly calculate the pressure at 2 according to both of these approaches. Okay, so the full hydrostatic equation, we have to know Z1 and Z2. And what I said was, let's have the bottom of the tank be 0. So then that makes Z1 is 50 and Z2 is 15, right? You could have said that 0 is the top, is the water, and then that would have made Z1 0, and then Z2 would be negative 35, but that seems a bit weird to me. So that's why I said we'll have the bottom of the tank be 0, and then the other two would have a positive elevation above that datum. Okay, so you have to have Z1 and Z2, and then you have to know the unit weight. Here it says that the tank is full of water. It doesn't say the temperature, so we'll just use the default value of 9810 newtons per meter cubed as the gamma for this liquid. And then finally, the P1 we know to be, in terms of absolute pressure. Anybody remember what atmospheric pressure is in terms of absolute? Good. 101,000 pascals, or newtons per meter squared. If we're being exact, it's 101,325 newtons per meter squared is in terms of absolute pressure. That's what the atmosphere is at sea level. What about at gauge? What's the gauge atmospheric pressure? 0. So it's the pressure relative to itself. So gauge pressure means we're using atmospheric pressure as the starting point. It's the datum above which you'd measure any additional pressure. So here at 1, the gauge pressure is 0 because where the water is touching the air, they have the same pressure. You know, when two fluids are in physical contact with each other at the same elevation, then they have the same pressure. And so the water pressure at 1 is equal to the air pressure at 1. So let me pull up the solution and show you this, the left side here, the full hydrostatic equation. What I said is, is this right here for the elevations? 34 and 26. I don't know what I was thinking, why I did that. Because it should be 15, and I wonder if I've got the wrong problem up. Oh, okay. Just need to scroll down a little bit. 50 and 15. Thank you. I'm losing my mind. All right. So here's the full hydrostatic equation. Rearrange the equation to solve for P2. And so move all the other variables to the right side. In terms of gauge pressure, remember when we're solving for gauge pressure, that's when we say atmospheric is 0. And so we set P1 is equal to 0. We have the difference in elevations, and then you should get 343,350 newtons per meter squared is the gauge pressure. And then the absolute is when I add atmospheric on top of it. So that's when I'm adding on another 101,325 pascals. So the absolute pressure at 2 should be 444,675 pascals, according to the full hydrostatic equation. Pardon? Yeah. So there's two ways of looking at what is the pressure here at the top of the tank. We can either measure the water pressure here at the top of the tank according to what if we were in the vacuum of space. In the vacuum of space, or we can measure it relative to the atmospheric pressure. And so our Earth's atmosphere is 101,325 pascals above the vacuum of space. And so here, if we're talking in terms of absolute, there's no pressure there. There's just the atmospheric. It's either 0 if you're using gauge pressure, or 101,325 if it's absolute. So now the abbreviated version of the hydrostatic equation, we just have the change in pressure. So the delta P. So it's the delta H, so the distance in elevation. The difference in elevation is 35 meters. Multiply that by the unit weight. So we get the same answer either way, is the point. Okay, so are there questions about the hydrostatic equation? Well, here's the next logical extension of the hydrostatic equation, and that is, what if you have two different liquids in contact with each other? Let's say, for instance, here that we have an oil floating on top of a water. The main principle is that pressure is additive, that you continually accumulate pressure as you work down through the fluid. And you can apply this abbreviated hydrostatic equation anytime you've got liquids in contact with each other. So we could do it in steps. If we wanted to find out, for instance, what is the pressure at the bottom of the tank, let's say that this tank has a total depth of 4 meters. You know, both liquids together, the depth is 4 meters. So we have a layer of oil that's 1.1 meters, and then we have water below it. And we want to find out what's the total pressure at the bottom of the tank, gauge pressure. I put that in parentheses. So what do I mean when I say what's the gauge pressure? What's the implication? What do you have to assume when I'm asking for the gauge pressure? Atmospheric is 0. So what that means is assume that here at the top of the tank, since that's open to the atmosphere, pressure is 0. And then as you go down through the oil, the pressure will accumulate, and you've got to stop at the interface. And then you keep working downward, applying the hydrostatic equation. But why? I'll give you one of the main ideas here. You can't go all the way from the top of the tank to the bottom of the tank in a single step. You have to do this and break it up into 2 steps. So looking at the equation, anyone want to take a guess on why you have to do it in 2 steps and why you can't apply that hydrostatic equation in a single step?
2 different unit weights.
You've got 2 different unit weights. So if you were doing it as a single step, what gamma would you use? Would you use the oil, the water? Maybe someone creative is thinking, well, I could come up with like an average unit weight, but no, don't do that. Just do it in 2 steps, and you'll always get it right. All right, so let me pause the recording, give you a moment. Now there's a built-in trick here. It's not a trick question, but I have intentionally not dimensioned that drawing, so pay special attention to getting the delta H's correct that you need on this problem. And calculate the gauge pressure at the bottom of the tank. Again, as a reminder, gauge means assume the pressure is 0 at the top of the tank and then increases as you work downward. We've got a lot of examples. All right, so you'll notice I did a sketch. Most of your sketches look better than mine, especially the ones who are doing it in like color, different inks and everything. But the thing you have to be careful about in the dimensioning is you want to know what's the thickness of each layer, not the total thickness. And so I intentionally didn't tell you how thick the water layer was. I told you how thick the oil layer was, and then the total thickness of both liquids was 4 meters, and so you got to use subtraction to find out this 2.9 meters between location 2 and location 3. And here I've labeled these locations because what I'm saying is I'm going from 1 to 2 and then from 2 to 3. So it kind of helps me to keep track of its 2 different steps. And so starting at the pressure at 1 is 0. And then I'm applying the hydrostatic equation. I'm saying the pressure at 2 is whatever the pressure was at 1 plus the change between 1 and 2. Now, we're given the specific gravity of the oil. And what you need is the specific weight, or the unit weight of the oil. So to know the gamma of oil in terms of newtons per cubic meter, you have to multiply that Sg by the gamma of water, because Sg is the ratio of your density or your specific unit weight or your density relative to that of water. And so that's why we've multiplied those 2 factors together to get the gamma of oil. So the pressure at 2 should be about 8,000 pascals, and then the pressure at 3 is the pressure at 2 plus the change between 2 and 3. And so we have some new increase, that is the 2.9 meters of water And so 2.9 meters multiplied by the gamma of water means an additional 28,449 newtons per meter squared. So we add that increase in pressure to the pressure that was at 2, and then the sum total of those is 36,542 pascals. Let me zoom out a little bit so you can see it all at once. The concepts aren't difficult, but you know, it's easy to make mistakes. Our exams this semester are going to have some multiple choice questions and some questions where you work them out and I'll grade and give you partial credit. And the reason for that is I want you to start getting acquainted with the format of questions that you'll face when you take the Fundamentals of Engineering exam. I work on the committee that writes the FE exam, and so I've written a lot of FE questions over the years, and so I want some of your exam questions to kind of mimic that same approach and pattern that will be used on the FE. And the reason I bring it up now is that it requires an attention to detail. In addition to understanding the fluid mechanics, you also have to be pretty careful with your calculations and avoid mistakes to get those problems right. And it's natural for engineers to be expected to be really precise and double check, triple check your calculations because people's lives are on the line with the things that you build, the machines that you build and the infrastructure that you're designing. There's a lot at stake there. So to get some of these problems right is partly about understanding the fluid mechanics, but then it's also about maybe avoiding mistakes. And one of the great ways you can avoid mistakes is to include your units in every step of the calculation. And if you don't have the units, then it's too easy to multiply numbers together that shouldn't be multiplied together. And for instance, here I'm using the newtons per meter cubed instead of kilograms per cubic meter because I know that I need the gamma of water, not the density of water, and so on. So I'll try not to lecture you too often about how important it is to include the units when you write your calculations, but it is something I think is really useful. So any questions on this example before we move on to the next? Simple ideas, right? All right. Now, this is, I think, kind of a fun idea, the idea of pressure transmission. And it's, in some ways, a little bit counterintuitive. So those are always the fun things, is the things that at first glance seem a bit odd. Now, the way that a car lift works, such as this, is that you have a compressor. Maybe it's not shown on the screen here, but what we're saying is we have air that we're just taking from the atmosphere and we're compressing it through this piping system into the head space above a hydraulic oil. And the purpose of this hydraulic oil is just to transmit pressure. And so the air is pushing down on the oil interface, and then the oil has all this pressure, and the oil is pushing up on some metal cylinder. And since the interface of the oil on the left side is at approximately the same elevation as the interface on the right side, the magnitude of the pressure pushing down from the air on the oil is the same as the magnitude of the pressure of the oil pushing up on that cylinder. And so the key point here in pressure transmission is that you can move where the pressure is accumulating to where you want it applied. We have some compressor in a storage room someplace, and that's providing the ability to lift up a car where the oil is pushing up on the cylinder. Now, from a mathematical standpoint, you can calculate the magnitude of the force. Look at the units. We know force has units of newtons. Pressure has units of newtons per meter squared. And so if we multiply a pressure by an area, then that will tell us the force that can be lifted. So this car is presumably pretty heavy, right? And its weight is acting downward. And we want this system to push up so that it can lift the heavy car. So there's going to be a force applied upward on this cylindrical metal shaft. The oil is going to be pushing up with some pressure, and we have to consider the area that that pressure is acting over. And then that will tell us the force that can be lifted. Okay, so let's throw some specifics in here. Let's say that this cylinder has a diameter of 25 centimeters. So that metal cylinder, the bottom face of it is going to be circular. And so we can calculate the area. In fact, that's already been done for you there, just to speed things along a little bit. So we have a certain diameter that gives us a cross-sectional area on the bottom of there. What if the pressure of air inside of that tank is 600 kilonewtons per square meter? So that is the pressure of the air down on the oil. And like I said before, also the oil is pushing up on that circular face with the same pressure. So what force can we lift up? Just punch that into your calculator real quick. Pressure times area. Anybody willing to tell us how many newtons we've got? 29.5 kilonewtons. That's right. Exactly. So let me show you the solution. Now, I've got a little drawing here. It kind of illustrates the main idea. The main idea is we've got air pressure pushing down, which results in the oil pushing up. We've got some face that it's acting over. And so the pressure is 600,000 newtons per meter squared. The area is 0.04909 meters squared. So here's our force. So that's the magnitude of the force. Now, in SI units, that amount of force is equivalent to about 3,000 kilograms of mass. So we're talking about it could lift a vehicle that's roughly 6,500 pounds, maybe 7,000 pounds, pretty heavy, like a Mercedes heavy, right? So now I have a couple of follow-up questions here. We calculated what the force is, the force that's lifted up under these current conditions, but what if we turned the air compressor on? What would happen to the system? I mean, you know instinctually what's going to happen if you turn on the air compressor, right? Is nothing going to happen? The car goes lower or the car goes higher? It goes higher. How come? Why? Why does the car go up? All right, good. So you turn on the air compressor, you've got more pressure in here, so more pressure in the oil, more pressure up. So if you turn on the air compressor and it went from 600 kilonewtons per square meter, what if it went to 605? Does that mean that this lift is going to, once you turn it up to 605 and it's the same car, let's say that we had that same force, like the weight of the car that we had before. So we didn't change the car, we just turned on the air compressor a little bit until it was 605 instead of 600. Is it going to keep lifting forever? What's going to happen? Okay, you'd run out of like the physical limitations, but like perfect equilibrium, right? So it's going to get to a point where I wish I had a marker today. It's going to raise a little bit higher, but then it's going to stop because the extra 5 kilonewtons is going to be the pressure. You've got one? Man, you are prepared. You must have been a Boy Scout, huh? That's excellent. I was too, but I didn't bring a marker. All right, so here we go. So we've got a little bit of all right, so here's the oil. So if we put on some extra pressure, it would cause an additional deflection. So that extra pressure would be delta H times gamma. is how it would work. It would come into equilibrium, and so if I added an extra 5 kilonewtons of pressure, then I'd need to know what's the unit weight of the oil, and then I could find out how much higher the car is going to get by simply having the delta P divided by the unit weight of the fluid. And then that would tell me the additional deflection until it came into equilibrium. I see a lot of heads nodding, so that makes sense to people. That's what would happen if we turned the air compressor on. What if, here's a fun what if instead of 25 centimeters of area, what if the diameter was 50 centimeters? Anybody want to speculate on what does that mean if we had a bigger cylinder than what we've got now? What? More force? Yeah, if we look at this equation here, force is pressure times area, so it would have a greater lifting capacity. You know, let's say the compressor can still get up to the 600 kilonewtons per square meter. So we didn't change the compressor, but we doubled the diameter. So how much extra force could we lift if we doubled the diameter? How much? No, not twice as much. That's a trick question. Yeah. I specifically said doubled because I was trying to lead you down that road. Because if we double the diameter, what do we do to the area? Yeah. So area is pi d squared divided by 4. So if you go from 25 to 50, so you double the area, you double the diameter, it's 4 times as much area. So it would go from 600 kilonewtons of pressure, but the lifting capacity, what did we calculate it was? 29,454 newtons. So approximately 30 kilonewtons. It would go from 30 to 120 kilonewtons of lifting capacity. So we quadruple our lifting capacity by doubling the area, doubling the diameter, because diameter squared gives you the area. Yeah?
So if we have the same amount of air, let's say air is, we've got it set.
The same pressure?
Number, right.
Okay.
With this tube, and then we replace it with the larger tube, it wouldn't go up as high, right? Or would it?
Well, it depends on what's on top of it.
Okay. So
Yeah.
is this similar to the capillary effect when you have a large?
No, this isn't the capillary effect. We will talk about that. I'm glad you brought that up because that's an important thing, and we will get to that maybe even in this chapter. Yeah. So. Okay. Other questions? Yeah. Yeah. So what we're saying is, you know, I posed the hypothetical question of what if we turned the air compressor on. So this equation on the board, we're trying to find out. It's in equilibrium as pictured. Let's change things by turning on the compressor and adding more air pressure. So what's going to be the new equilibrium? This equation on the board, the hydrostatic equation, tells us how much extra height we'd have. You know, how much higher this car would rise if we put in a little bit of extra pressure. And so what I was saying is, if you start with the hydrostatic equation and rearrange it for delta H, then it would tell you some additional pressure inside of that headspace above the oil, divide it by the unit weight of whatever the fluid is, would tell you how much extra deflection you'd get by increasing the pressure. Any other questions before we move on to the logical extension of this pressure transmission? The logical extension, of course, being the hand jack. This is one of my favorite illustrations of the semester because it combines a lot of what you learned in statics with some of the ideas of fluid mechanics. I hear lots of snickering. I'm not sure why. Statics feels like a long time ago maybe, right? All right, so we've got a jack here. And so the way this jack works is we want to lift something over here on the right side. Let's say it's that Mercedes. You know, we're trying to lift it up so we can change the tire. The way that we're going to lift a super heavy car with just the force that you could exert with your hand is we need to magnify our lifting abilities. And here you're magnifying it two different ways. One is with the mechanical advantage of this moment, the difference in moment distances. We're going to be pushing down really far away from this pivot point at C, but we're pushing it down far away, but it's pushing on the liquid a little bit closer. So that's one of the ways that we get some leverage and mechanical advantage. And then the other is the difference in areas. Now, I'm going to take you through this illustration step by step, just so that you can kind of see what I've got in mind here. All right. The first thing I'd like you to consider is, I'll do this with the marker since I've got it. That's great. All right. Let's draw the handle. So in your notes there, draw, we've got a handle, and it's connected at C, and we've got some force that we're pushing down. If the force at F is 100 newtons, so we've got this 100 Newton force acting downward, and then we've got this, I'm going to call it F sub B, acting upward on the handle. So we're just thinking about what's happening. It's probably like some sort of a steel rod of some sort. We're pushing down on the steel rod on the handle, and then this plunger system is going to be pushing up on the steel rod, because think about when you start pushing down, we know that it's going to be pressurizing the fluid inside of that jack. And so when you push down, it pressurizes the fluid on the jack, and the jack is pushing up at location B. So that's why I've called this F sub B. Now, the moment distances that we have to be aware of is it's 3 centimeters from the pivot point at C to where force at B is applied, and then a total of 33 centimeters. So this distance here is 33 centimeters. And of course, that's like another point of caution. Is it saying 30 centimeters from B to the handle, but the overall moment distance from C to the point of application of the force is 33. Okay, so with this little sketch that's on the whiteboard, what does that allow us to calculate? Yeah, it allows you to calculate F sub B. So what we know is F times 33 centimeters will equal F sub B times 3 centimeters. All right? So this is our first kind of mechanical advantage step here. That is the force at B. Let me scroll down to that. For those watching at home, all right, so we've got our handle, applied the moment analysis about point C, and the force at B should be 1,100 newtons. Now, that force at B is going to allow us to find out the pressure inside, the pressure of the hydraulic fluid in the jack. How do we go from a force to a pressure? What's the formula that relates those two things, force and pressure? Area is the missing link there, right? So pressure is force divided by area. So we know that we already drew the handle part. The next part that you should draw in this example is like the little plunger. It's like this metal piece that it has the force coming down of 1,100 newtons, and then it's got some area that it's distributing that force over. And we're going to call that A1, just as it's shown there. The drawing says it has a diameter of 1.5 centimeters, and so we can calculate A1 according to the formula pi d squared divided by 4. Okay, so that's pi and 0.015 meters squared divided by 4. Okay, so in terms of square meters, then the area is going to be 0.0001773 meters squared. That's the area. The reason why we need to know that area is because the force is being spread out over the contact of that steel plunger with the hydraulic fluid inside of the jack. So if it was a really big area, then that would make the pressure smaller. But if it's a relatively small area, then you've got a lot of force over a small area, then the pressure is going to be high. So if you think about conceptually, how do we make this jack lift something really heavy? Well, you'd want a long handle. That would help. And then the other thing is you want A1 to be small and A2 to be big. That's the ratio of mechanical advantage on the hydraulic side of things. The ratio on the handle side of things is that you'd want the distance between the handle and B to be long and relatively short between B and C. That's how you'd amplify lifting ability. Okay, so we calculated the area, and now let's find out the pressure in the fluid. The pressure is the force divided by the area. So the force was the 1100 newtons, and the area is 1.773 times 10 to the minus 4th meters squared. So it's going to be 6,225,000 newtons per meter squared. So really high pressure inside of there. And from a practical standpoint, you need to ask yourself, can the seals that go around that plunger hold a pressure that high, or is it going to start leaking hydraulic fluid around the fittings inside of the cylinder? Okay, so here's the little sketch of that metal piece where the force is being turned into a pressure. Force divided by an area. We need to calculate the area so we can find out the pressure inside of the jack. So what do you think we do next, now that we know the pressure of the fluid? Yeah, so we have to take a look at A2. Exactly right. So what are we going to do with A2? We've got a pressure. We've got A2. Solve for force. Right. So force, in this case F2, is simply going to be P times A2. All right, so as the final step, I'd like you to do that. We've got the A2 is, you need to calculate that based on 5 centimeter diameter. I'll walk around. I've got the solution here in my hands. I want to see if you can find out the force at 2 that can be lifted by this jack, given the pressure that we know inside of the fluid. All right, so we started off with the force on the handle, turned it into the force at B that would result for this handle to be in equilibrium. Okay, so if the force at B is 1100, then that means that the force up is the same as the force down on the plunger. And we can know with the area what the pressure is going to be in the fluid by having this force applied over some area. And so the last thing is for us to look at now this larger area at 2 and find out how much load the jack can lift. And you should get around 12,000 kilonewtons. Who got around 12,000 kilonewtons? All right. Very good. So it's amazing if you think about what it was able to do. We're just pushing down with 100 newtons of force, and it's lifting 12,200 newtons of force here because you had the magnifying the force with the jack arm and then the difference in the areas. And so if you wanted to lift even more than that, you could either lengthen the handle or you could make A2 bigger relative to A1. Or you could make A1 smaller and leave A2 the same. And that would have the same effect. It would allow you to lift even more with the jack. Are there questions about this example? Yes? Yeah, it seems like I might have done some round-off error on my solution. On mine, let's go back to that. I'm going to double-check these numbers after class, and I'll let you know. But was it the area at 1 that you were getting different?
Yeah, and then it made the pressure off pretty much.
By how much? Percent-wise? I'll double check my numbers. I like it to be as exact as possible, but I think it turns out to be maybe 1 or 2% difference. Yeah. So hopefully, I mean, it doesn't turn it into the realm of the outrageous, but I am going to redo this example and double check the precision of my area. Okay, one last thing I want to go over before we break for today. That is the beginning ideas of manometry. Let's say that we have water flowing through a pipe, and this is a pressurized pipe. Now, the way this drawing works, what they're intending to illustrate, like the little curved figure on the end there, it means that the pipe continues in both directions. So it's not like we just have some magically isolated piece of pipe that has water in it. So the pipe continues in both directions, but what we're looking at is just a segment, and if we cut a hole in a pressurized pipe, then the water would spray all over the place. So here we've got our pipe, and let's say we just poke a hole in the pipe, then the water starts spraying everywhere. But what this drawing is saying is instead of doing that, instead of just having it open to the atmosphere, instead, what if we had a tube going upward? What would happen is, remember the water inside the pipe is pressurized. The water level would rise to a certain elevation, and then it would stop rising. It would come into equilibrium. And the equilibrium that it would come into would depend on the difference in elevation between the 2 points. And so we would have this same relation, delta P is delta H times gamma. And so whatever this fluid is, if it's water, then the water level would rise to a certain elevation that would be dependent on the pressure of the fluid inside of the pipe. So this is a piezometer, and it's one way of measuring pressure in a system. It only works if the system is a liquid, because it wouldn't work if it was a gas. And if this was a gaseous fluid and you poke a hole in it, then the fluid wouldn't stop rising at a certain elevation. It would continue to disperse out into the atmosphere. But if this was a liquid and our H is 10 meters, then you could use that as an indication of how much pressure is inside of the pipe. It would be a way of measuring it. And so in this case, if you had 10 meters of elevation, and you know the liquid was water, which has a unit weight of 9810 newtons per meter cubed, then this would be a way of measuring the pressure to be 98,100 newtons per meter squared. So the typical water pressure in a municipal system, the pipes that are running through Huntington, on the low end, about the lowest pressure they like to have in the pipes is about 200,000 kilopascals. And it would go up to maybe around 200,000 pascals, not kilopascals. So the typical range of pressure would be 200 kPa up to a maximum of about 850 kPa. And they don't like it to go too much higher than that, because then fittings can start to leak. And one system in the home that's particularly vulnerable to high pressure is water heaters. They would start to leak first. So think about what that means. If we were trying to measure the pressure in water pipes under the road using piezometers, what we would have to have. If you had a system with 850 kilopascals, you'd have to have an awfully tall pipe to be able to measure that. You know, the delta H that you would need to measure a pressure of 850 kilopascals. So let's actually rearrange that equation. So delta H will be delta P divided by gamma. So it would be 850,000 newtons per meter squared divided by 9810 newtons per meter cubed. So what would be the delta H? Somebody with a calculator tell us the height the water level would rise to in a piezometer connected to a pipe with that much pressure. 86 meters? So that's like almost a football field. And people would have to be walking around on awfully tall stilts to measure the elevation. It's not a practical way of measuring the water pressure in a system like what we're talking about. But this piezometer is very similar to the way that water behaves in soil. As it ends up, there's something called the capillary effect, where when you have a really small diameter tube, the water level rises inside of that tube. And we'll actually have an illustration of that in the lab later this semester, the capillary effect. And so piezometers end up being interesting and important for a lot of different applications, but not for the measurement of water pressures in a like a drinking water network, because the pressures are usually so high. Okay, well that is all for today. Let's end by going over a couple of key ideas. These are homework problems that I think maybe you'd like to have a few head starts on the ideas behind this, just to make it a little bit simpler to solve. You know, you're only required to submit how many assignments in the semester? 10. But you should still solve them all. I think that it's going to be valuable for you, particularly to review the solutions that the grader has posted. How many of you have looked online to see that your homework's been graded, your first assignment's been graded, and what the grader will do is tell you which problems you got wrong? And you should go to the solution that's posted there and try and figure out, like dissect the accident, or like do a post-mortem, kind of an autopsy on how'd you miss the problem. And so even though you don't have to submit all your assignments, I'd encourage you to do those problems and to review the solutions that are posted. Okay, so for this, what I wanted to do on this key idea is help you interpret some of the language that it gives you in the problem statement. It says that the air pressure inside of this airspace is 50 kPa vacuum. Now you can see that the water's getting sucked up into that tube, right? What does this triangle and the little horizontal lines mean? In contact with the air. So what we have is air that's touching the water, and then if you go down in the tube, the pressure is increasing. If you go up through a liquid, what happens to the pressure? Decreases. So right here, inside of the tube, the pressure is equal to 0. But as we keep going, 0 gauge. As we keep going up, now it's negative gauge pressure until we get to here. And so you can kind of visually see in this that there is a negative air pressure inside of that airspace zone. And the way that they are describing it is they're saying that it's 50 kPa vacuum. So that means it's 50 kilopascals less than 0 pressure, where we're saying 0 gauge pressure. It's not below 0 absolute. You can never go below 0 absolute pressure. But you can go below 0 gauge pressure. So the way that you should think of this problem is that the pressure of the atmosphere is 100 kilopascals absolute. And I think in the problem statement, they may tell you that the water is at 20 degrees Celsius, or maybe I'm just telling you that now. But for whatever reason, assume that it's 20 degrees Celsius water, So you can look up the unit weight from that in the back of the book is 9790 newtons per meter cubed. So the hydrostatic equation is going to apply here. We've got some H that the water level is rising because of the difference in pressure. So there's the pressure here and the pressure inside of the airspace. So in the airspace, the pressure is the same everywhere. Gases, the pressure changes a lot more slowly vertically through a gas than it does in a liquid. So you can assume that the pressure at the top of this little airspace is the same as the pressure at the interface of the gas and the liquid. So everywhere inside of here is 50 kPa as pictured, and it rises to H. And then what they're asking is, if you change the vacuum to 25 kilopascals vacuum, will it increase or decrease? So that's less vacuum than it was before. So here's the steps I'd suggest you consider. First, find out what was H when the pressure was 50 vacuum, meaning 50 less than 100. And then you find out how much does the water level rise when that vacuum is only 25 instead of 50, which is what it was before. And then they're asking you to find out what's the difference between the two. Any questions about this problem? Okay. So we've got a drawing here, and this is similar to the pressure transmission we were talking about today. You've got some weight, which you can find the force from a weight. How? What's the relationship between weight and force? Gravity. Yes, so if you've got the weight that's given to you, actually weight and the force are the same, but probably what they give you is the mass of it. They're calling it 5 kilograms. And so you can turn that into a force by multiplying it by G. So we've got some force acting downward, and then there's this metal piston, and the diameter is specified. So this is hopefully should be looking pretty familiar. You've got some diameter that you can find the area from. You've got a force applied over that area, so you can have pressurized fluid. But now what they want you to do is find out H2, where H is the distance from the interface of the piston and the liquid, then on the right side up to where it's open to the atmosphere. So the key idea I wanted to remind you of this is that you can use the delta P starting either from the atmosphere and then going down, or the other way of thinking about it is that the pressure here on the left side and here on the right side, that's the same pressure, because we go down and the pressure increases, sideways nothing happens to the pressure, and we go up, the pressure is decreasing. So the pressure is the same here and here. So you calculate the pressure on the left side, and then that tells you what it is here on the right side as well, and we know that the pressure is 0 at the top. And so you can just find delta H by rearranging the hydrostatic equation. Any questions about this one? All right, one last problem I wanted to give you a preview of. This one's tricky. All right, so we have a dome. You got to think about this in 3 dimensions. What it is it's like a hemisphere. Okay, so it's not just a circle, but rather think about if you cut a sphere in half. The cross-sectional view of it looks circular, but hopefully with all my hand gesturing here, you get the idea. It's like it's a basketball we cut in half practically. All right, so we've got a metal dome that has a weight of 6 kilonewtons. That's going down. But these bolts are here, and if they weren't, water would leak underneath. So the purpose of these bolts is to pull down even more, because The water is pressurized by the fact that we've got this tube extending upward. Now, the L that they're referring everything to, turns out we need L to be 80 centimeters. And so from that 80 centimeters, you can find out what is the depth from where it's open to the atmosphere all the way to the bottom of this weird-looking tank. So you can find out the pressure that the water is pushing down on the table. But the thing is, if we do a force balance on the system, if the system is the water and the dome, then this table or the ground is pushing up on the system with the same pressure at the bottom that the water is pushing down and the weight of the dome. So what I think you have to do is think about a force balance in the vertical direction. And the bolts are going to be a part of that force balance. Because what we need to do is find out how much force downward is required from the bolts so that everything else is in equilibrium. So think, what are the components in the vertical plane? We've got the only thing pushing up is the effective force of the ground pushing up. And so there's going to be some pressure on the bottom of the tank acting over the area of the bottom of the tank. And so the pressure at the bottom of the tank, the way that you can calculate that is with the hydrostatic equation. Delta P is delta H times gamma. We know it's water, so you can use the unit weight of water. The weight of the water, you can calculate that by the volume of a hemisphere and also the volume of this tube. So the weight of the water you could calculate. The weight of the dome is given as 6 kilonewtons in the problem statement. So there's this vertical equilibrium where the only unknown is going to be the force of the bolts. And that's what they ask you to calculate, is how hard do the bolts have to pull down so that all of the system is in equilibrium. I think the trickiest thing to kind of get with mentally is the idea that the table or that the ground is pushing up. Something has to be resisting all of this weight that's acting downward. And if the system is what we're trying to do an equilibrium on, the system being the metal dome and the water, then of course there's going to be a pressure acting over an area that is that force upward. All right. So I hope that gets you in the right direction. Just one last look at these announcements. You've got until 2 o'clock. We have lab today and tomorrow. If you don't remember what time you're supposed to go to lab, I've posted the assignments on the 319 website. So I'll see you at 2 o'clock or 3:30 today or tomorrow, depending on which group you're in. Have a good day.